and there are very kind of limited parameters you could model, cubic, quadratic.
Right.
But once if somebody does weird stuff, like goes up and levels off,
Yeah.
then we're in a new kind of design or new approach.
Well, yeah, you can use multiple predictor variables at level 1 to model these weird shaped curves.
I see.
It's just a use of multiple polynomials. You're fitting multiple polynomials. And there are other things you can do. You can do transformations like log transformations and things. So you can simplify this somewhat. You get log variables or that kind of thing to simplify the number of variables at level 1. To fit the data better.
So the assumption we're making here is they're increases their basic data.
We're keeping it really simple, where we just have two outcomes at level 2. We have intercepts and we have slopes. And we're not doing acceleration. We're going to do that this afternoon. Actually, Takashi's going to do that this afternoon in the lab, where you're modeling a linear and a quadratic component in a growth curve analysis. But we're not doing that here. So on average, Spanish speakers' knowledge increased 0.18 loads per month, faster than the English speakers' knowledge. Let's see. Okay, I went too fast here. That was initial status. They were not significant. We put the predictor variables into the equation to predict initial status, and they were not significant. Now you can come to the lab late. Okay, we'll finish this up so you can go to lab, and you can start lab at 1:30 or something. We'll start lab late so we can finish this up. So now the outcome is growth rates. The outcome is the growth rate. So why is it some kids have steeper trajectories than others? And so we put home language into the model to predict growth rates. We put hours of instruction into the model to predict growth rates. And we found that, that language predicts growth rate, statistically significant, and hours of instruction predict growth rate. So growth rates were significantly related to both common language, where Spanish is coded 1, English coded 0, and to hours of instruction. So the relationship between home language and growth rate is positive. So how do we interpret that positive coefficient of 0.187?
So if they were Spanish speakers, then they were a little faster in catching up.
That's right. So the Spanish-speaking kids started out lower, a little bit lower. They weren't significantly lower than the English-speaking kids. They started out lower, but they're growing at a much faster rate, a significantly faster rate than the English-speaking kids. So they're catching up very quickly. Within a very few months, they started out at negative 0.46 logis, and they're catching up at 0.187 logis per month. So within like 2.5 months, they're caught up to the English-speaking kids. So that's good news. So the trajectories are a lot steeper than they are for the.
Is that holding constant the effect of initial status and hours at 0.187?
It holds constant hours, but it doesn't hold constant initial status. Initial status is a dependent variable. Well, it's not in this case. It's a slope, but it's not. The intercept is not considered here. All we're doing is looking at the slopes. The intercept has nothing to do with this. Yeah, but we are holding hours of instruction constant. So assuming that they receive the same number of hours of instruction, the Spanish-speaking kids are growing at a faster rate than the English-speaking kids. They're catching up very quickly. On average, Spanish speakers' knowledge increased 0.187 emojis per month, faster than the English speakers' knowledge. Knowledge scores for a child who receives 40 or more hours. And then we look at the effect of hours of instruction on the trajectory. So kids that get lots of hours of instruction, do they grow at a faster rate than kids that don't get intense instruction? That coefficient is small, but it's statistically significant. So what it's saying that 0.00047, that's per hour. So if we gave the kids 40 more hours of instruction in a month, then we would expect 40 times that value, or 0.019 widgets per month, faster than a child who did not receive those additional hours. So hours of instruction is having an effect on their trajectories, on their growth rates, which is good. Trajectory is everything. You start here, but in a period of 12 months, it's where you end up is really dependent on your trajectory. So how much of the variance is explained? This is proportion of variance in y-intercepts. The initial values is explained by home language and hours of instruction. So the tau that's unconditional without those predictive variables in the level 2 equation for intercepts. We have a tau with the predictive variables in the equation, divided by tau without the variables in the equation. So the standard ratio that we've been calculating all along. And we started out with a tau of 1.689, and the tau, when we put those two predictors in the equation, drops to 0.76. That should be 1.869 in the denominator. That's a mistake. Cross that out with 1.689, and you end up with 0.549. This is right from the textbook, so I know that number is correct. So 55% of reliable variance in the initial status is explained by the language and hours of instruction. So this was our Venn diagram for y-intercepts, which consists of tau and error variance. We put these variables into that model to account for variance in y-intercepts. We're accounting for 55% of the true square variance in y-intercepts. This is wrong. This is wrong, wrong, wrong. And the reason it's not wrong, it's right. It's not right. I'm just repeating what was in the textbook. We put it up. I put it up there because we had it in the textbook. But you would not do this analysis. You wouldn't be looking for portions of variance explained in tau because these variables did not account for variance in tau. When you did the fixed effects test, we tested for hours of instruction, the effects of hours of instruction, and the effects of home language on intercepts, and they were not significant. So we've already concluded that these variables are not related to intercepts. So you wouldn't do what Frank and Rodbush did and calculate the proportion of variance explained by these variables, because that's misleading. You're telling people you're accounting for 55% of the variance, when in fact your statistical test said that there was no relationship there. You're not explaining any of the variance that you're supposed to do. So this is a mistake. They should not have done that. But at least recognize that, we'll do it for an illustration. We'll calculate it and show you how it's done, but we wouldn't ordinarily do this. It would be misleading. Does that make sense? You don't report effect sizes for things that are not significant.
So it's sort of like when you get an R squared, but in your model is significant, but none of your predictors are significant?
Yeah, that can happen. That happens with multilinearity. When the predictive variables are highly correlated, then you can get R squares, multiple R squares that are significant, and none of the regression coefficients are significant. That's a consequence of multilinearity. We would want to calculate the proportion of explained variance in these slopes. That makes sense because those predictive variables were significantly related to slopes, the trajectories, so we can calculate the proportion of variance in slopes, or it is explained by the two predictive variables. We take the tau without the predictive variables, the tau with the predictive variables, and divide by the tau without the predictive variables. And this is right, we got the right denominator. And so we're accounting for 75% of reliable variance and growth rates. 75% of the reliable variance and growth rates is explained by common language and by hours of instruction. So that's pretty good. So when we're analyzing growth rate as a dependent variable, we're accounting for 75% of that tau, the true square variables, growth rates. Questions about that? Okay, so anyway, we'll meet in the lab at 1:30, and then I guess Takashi can go through the growth rate stuff, and then I'll do a little section on meta-analysis in the lab. Unfortunately, we haven't introduced meta-analysis in class, so it's going to be one of those situations where the card becomes a course, but we'll talk about meta-analysis first thing tomorrow. So the first hour or so, we'll just go through that. And then I've got a student response system where we each get a little clicker thing, infrared remote system, handheld system, and I'll present questions. I'll give you an oral exam. And you each have a clicker, and so you'll register your answer to the questions A, B, C, D, or E, or true or false. And then I'll present a bar graph that shows the distribution of students' responses to the various questions that we have as a source of discussion. So you can do some self-testing to see whether or not you understand what we've been doing this week, and without feeling bad because nobody else